Hello, everybody, and thank you for joining us on today's webinar for solar water pumping for off-grid applications. We're going to give folks just a couple of more minutes to come on in, and then we'll get started at about a couple minutes after the hour. Okay, it's a couple minutes after the hour, so we'll go ahead and get started. My name's Errol Rankin. I'm going to be working together today with David Love to give this presentation to you guys on solar water pumping for off-grid applications. SunWize Power and Battery has been around doing off-grid solar design for almost 25 years now. We do a range of pre-manufactured and custom standalone PV hybrid and battery backup systems. We've got offices throughout the country, primarily on the East Coast and West Coast, with manufacturing and fulfillment in Oregon, California, and New York, with sales scattered throughout. In addition to manufacturing standalone power systems, we also do custom solar modules, component sales, subassemblies, kits, contract manufacturing, and a variety of other services, including capability to manufacture to ISO 9001, UL 508A, and others. Do client consultation, system design and engineering, and a variety of other services as well. Our systems can be found in a variety of locations in all 7 continents. So today, the presentation overview, we're going to go through an introduction to solar water pumping first. Then we're going to review some of the fundamentals of solar water pumping to make sure we have the foundational knowledge we need to go through the rest of the presentation. Then we'll review some pumps information from the SunPumps manufacturers, SDS line of submersible pumps. And then we'll go through both the SubDrive and the Photon series of solar packs from Franklin Electric. And then we'll discuss the SunWize Water Pumping Kits, WPK, which are the solar kits designed to operate with the submersible pumps. We'll talk about that. And then we'll go over our WPK lookup tables that can be used to find easy water pumping estimates based on sun resources, total dynamic head, and other things. And then at the end, we'll go over some information on SunTech Drive. So water pumping is a broad topic that interplays with a lot of different industries, including water, wastewater, agriculture, mining, oil and gas. It can include small fountain pumps, large pond aeration, drip irrigation, sump pumps, and a variety of other things. This presentation is going to be primarily concerned with vertical pumping applications, as is commonly found in well pumping scenarios. So just a quick overview from a high level of some of the content that we're going to be going over today. There's going to be 2 lines of submersible pumping options, 3 actually. We'll be going over the SunPumps, which are 24-volt DC typically, with a maximum dynamic head of around 220 to 230 feet, and they produce approximately 1 to 4 gallons per minute. It's a relatively small size, relatively simple 1 to 2 solar modules. As you move up in size, we'll go to the Franklin Electric. Those come in 3/4, 1.5, and 3 horsepower versions and can go up to about 35,000 gallons per day. And then we'll talk about SunTech Drive, which is actually a controller that allows solar to be integrated with traditional single-phase or 3-phase AC pumps. Okay, so when operating solar water pumping systems in remote areas, no grid, defining the power source is obviously an important, critical first step. Solar is usually the best option for small to mid-sized pumping systems, and today's presentation is going to be focusing on system size for approximately less than 35,000 gallons per day. So solar is a great option because sun resources have a great symbiotic relationship with when water is typically needed. When it's hot and sunny and dry is oftentimes when water demand is highest, and that's also when the sun resources are highest. So some of the advantages of solar water pumping are that the solar resources are very consistent, at least compared with some of the alternative options. So that enables us to design quite accurate seasonal water flow estimates. There's no moving parts in the solar array, which makes the technology very reliable when compared to alternatives such as wind generators or traditional generators. Currently, we've had historically low solar module prices, which makes solar water pumping an extremely affordable option. And finally, we'll learn that batteries are not required for a solar water pumping system. We can use water storage tanks equivalently to have that energy storage, quote unquote, that we need, which is a much more cost-effective option. Okay, so the presentation goals for today are first and foremost, to understand how to calculate total dynamic head. And then we're going to use our knowledge about total dynamic head and seasonal flow rates to choose the appropriate hardware for our project goals. The hardware being the solar array components and then the water pump. And then we'll talk at the end about retrofitting existing pumps with solar, and that's primarily common single-phase, three-phase AC pumps. All right, typically the solar water pumping systems that we're going to be talking about are wired DC direct from the solar array to the water pumping controller. What that means is that water flows when the sun shines, meaning sufficient voltage and current to operate the motor and the controller. We have a learning page on our website under the main header drop-down areas. Under the learning section, you'll see there's a solar water pumping basics page. It has a lot of the information if you want to follow along for today's presentation. And you'll note that a lot of the fundamental work that goes into designing solar water pumping systems has to do with calculating and understanding your total dynamic head, TDH. So what is a basic solar water pumping system using a submersible water pump? It looks something like the diagram you're looking at on the page. We'll go over the major components here. Starting from the left, we have your solar array, which is basically your solar modules and a racking structure. And then that is wired into your pump controller. The pump controller is responsible for taking the direct DC voltage from the solar array and doing any sort of regulation or modulation to give the pump motor exactly the electrical specifications that it needs. After the pump controller, we have an optional DC disconnect, which can be very handy for maintenance and other things like that. And then below that, we have our water level. That's our water table below ground. And then we've got our well casing where the submersible pump goes in. And then we've got a water pipe that leads up to a tank, which could theoretically be optional. And then we have a float switch control, which is also optional. We'll talk about a little bit what that is. And then you'll see in the red in the center, we've got a diagram for total dynamic head, and we'll cover what that is. Okay, so just to cover the fundamentals again, solar array, pump controller, submersible pump, and water pipe. Those are your critical components that will probably be in all of your common systems. And then the optional components are the DC disconnect for maintenance and servicing, the water tank for storage capabilities, and then the float switch, which basically is an automated switch capability for the pump to give your water tank a minimum and a maximum water level. Okay, so the 3 steps for determining your estimated flow rates for your solar water pumping project estimates are first to determine your sun resources at your project site. You can use a map or a lookup table or a variety of other resources. And one of the questions you want to ask yourself is, are you trying to maximize your flow rates in the summer, in the winter, or on average over the entire year? And why are you trying to do any of this? Because as you'll see, that will change our design. Next step is to calculate the total dynamic head. This is really going to be kind of the meat and potatoes of the exercise. And then at the end, we can calculate our seasonal flow rate based on the information above. The formula for that is the sun hours at your site for either the month or season in question, times the gallons per minute of your pump for whatever curve specifications we identify, which we'll go over, times 60 minutes per hour, and that'll give you your gallons per day. Okay, so the first step is to determine your project solar resources. A couple ways we could do that. We recommend the NREL Redbook data is a great resource. There's also a variety of maps available. Be cautious on the maps that you're looking at the right map data. If you're looking for summer solar resource data, be sure not to use yearly average maps. The number you're looking for is a number between approximately 0 and 7.5, and that'll be in kilowatt hours per meter squared per day. That's your sun resources. All right, and then the next section is going to be calculating total dynamic head. I'm going to turn this over to my colleague, David Love, who has a ton of experience in this, and he can help walk you through calculating total dynamic head.
Thanks, Errol. Thanks, all. I'm David Love. I've been with SunWize for a couple of years, plus even longer way in the past. And I've done solar water pumping for well over 20 years. And the one thing I want to add on to the map that Errol just showed is also understanding what your client means by summer. I found that summer is a very variable description. Sometimes if it's a high pasture, it may be July and August. And then other times it's April through October. So really nail down what the customer means by summer. That's one place I found people fall off the racks. So much like remote off-grid power systems, the hardest part to do is figure out what the load is. And in water pumping, it is calculating what the total dynamic head is. And that's a new term for you and also especially for the end user. It's really a combination of the elevation that we're trying to pump it up from the pumping level plus the verticals, friction loss, and output pressure. And go ahead and flip to the next slide. So the one thing that's not on this list is well depth. That's typically what folks know of. I have a 200-foot deep well. It's mildly interesting. It's not very useful. It really has to do with the pumping level from where the water is in the well. It could be at 100 feet, it could be at 180, or it could be at 20 feet. So that's really the critical level to start with. And also in wells with a slow recharge rate, the drawdown can get significant enough to become part of the calculation. On a small sun pumps where you're running at 1 or 2 gallons a minute, it may not affect the drawdown. The drawdown may not exist because of the slow pumping nature of that pump. In higher ones, it needs to be calculated as well. So pump level plus drawdown is where the water level will be when the pump is in operation. Then we'll measure up to the top of the storage tank, to the elevation of the wellhead plus elevation above that to the water tank. And then also friction loss is the calculation of the friction loss in the well pipe from the wellhead out to the tank location. And in many cases, this is a pretty short number, but it's something to really keep in mind for long runs of water pipe between the wellhead and the tank, because if it's 10 feet, 20 feet, probably not a really big deal. But we've had cases where it's 3 miles. So that really requires looking at the peak flow from the water pump and the distance, and also the pipe size, and also if it's new pipe or existing in the ground. So it just adds up to be a larger load on the pump based on the friction within the pipe. So the calculation of all those together is total dynamic head. And in most water tank situations, there's no output pressure required. In others, there is. If you're trying to fill up a pressure tank and you're running that up to 30 psi, holding some water there, then that 30 psi is a significant load, because 1 psi is equal to 2.31 feet of head. So, running that up to 30 psi is adding an additional nearly 70 feet of head to the calculation. So go ahead. So yeah, just keep this kind of chart in mind, because the real red herring everyone gives is, total dynamic head is equal to the depth of the well, and that's seldom the case. In a lot of applications, you may never know what the well depth is, or the water level is within the well. And if you're dealing with one of the small SunPumps, it may not make a great big deal of difference. The SunPumps is a diaphragm pump which has a fairly flat pump curve, just meaning it'll do about 1.5 gallons a minute, regardless of where it is in the range. It's a diaphragm pump, and every time it goes around, it squirts a little bit more water out, and the change of total dynamic head within the range of that pump will not make a gigantic difference. Go ahead, Errol. So once we have all the calculations done, then we can take a look at what pump will meet both the total dynamic head range as needed and also deliver the water as required. Go ahead. So, and especially if you have questions on larger water piping situations, let us know, and we've got charts or there's online resources to calculate the long runs of friction losses. Just make sure everything gets covered. Go ahead, Errol.
Thanks, David. Appreciate that. I'll just point out, he didn't mention it explicitly. For the friction losses, definitely recommend using an online tool. There's a variety of them out there. If you look at this example, the result in that middle column where it says head loss of 30 feet matches the example here. So just a frame of reference for you to give you an idea. That's just one tool that we like. All right, so now that we've got the fundamentals out of the way, we're going to talk about our first pump manufacturer and a little bit more in depth about their SDS line. As David mentioned, that's a submersible pump product line. These pumps accept 12 to 30 volts DC approximately. As you'll see, they can label it up to 34 volts, which is actually what the max power voltage is from a 24 volt array. So we'll see that. These are designed for 4-inch inside diameter and larger wells. So you need a minimum of 4-inch inside diameter. These pumps will produce up to 4.7 gallons per minute and a maximum total dynamic head of about 230 feet. So in the whole grand scheme of things, are relatively small, simple systems. All right, so on this pump curve table, which is basically a table layout of the information on a pump curve for one of the SDS pumps. In this question, we're looking at the SDS D128. There are several tables for different voltages between the 12 and 30/34 volt range. Here they're listing it as a 34 volt panel direct. That corresponds to 24 volt nominal solar array. So a traditional 72 cell solar module or 236 cells wired in series. So I've highlighted a couple of the major columns in question here. So we basically have our total dynamic head column ranging from 0 to 231 feet. And then we have our gallons per minute at those various total dynamic heads. As David Love illustrated, you can see at a basically 0 total dynamic head, we only drop from about 1.5 gallons per minute to about 1.15 gallons per minute, going down to our maximum total dynamic head. So not a tremendous change. So in this question, our previous example, if you go back and review the slide, you'll note that we had about 141 feet of total dynamic head on that example. So I'm going to go ahead and run with that number approximately, just for a frame of reference. So we're going to choose the next closest total dynamic head of 139 feet, which is very close. So that's obviously in pretty close agreement. So we're going to go with an estimate of approximately 1.25 gallons per minute for that system. So what is the summary information? We have a total dynamic head off the chart of 139 feet. We have to determine our sun resources. We haven't specified anything, so I'm just going to make up a number. Let's assume that it is 2.5 peak sun hours average for the month of May for the site. So what we're going to do is we're going to calculate the seasonal flow rate. So we multiply the sun hours times the gallons per minute times 60 for our formula. You get 2.5 times 1.25 times 60, you get 187.5 gallons per day estimated flow rate production in May for this site. Okay, so if you go back to our curve, you'll notice that the last column here is the peak panel watts. So it's about 97 watts with about 30 to 34 volts. So we need about 100 watt solar array, and we can accomplish that through either two 50-watt modules, approximately 12 volt 50 watt modules wired in series, or a single 24 volt nominal 100 watt solar module. Either one of those will work. If we have that solar module in a location with sun resources of 2.5 sun hours per day for a given month at a total dynamic head of 139 feet, we can expect to produce about 187.5 gallons per day using the SDS D128, I believe. Okay, so that is a basic, simple overview of the SunPumps and the SDS line. Next, we're going to talk about the Franklin Electric series of photon and subdrive solar packs. These are also submersible pumps. I believe they are centrifugal pumps rather than diaphragm pumps, and they are relatively significantly larger in size. The flow rates for the Franklin Electric pumps go up to approximately 35,000 gallons per day, and you'll see from here they accept up to about 330 volts DC from the array. This is an image of a subdrive solar pack. This is basically what you get when you order a solar pack from Franklin Electric. You'll see that you have the submersible water pump and motor there, those cylindrical columns, and then you have the pump controller housed in that nice box. Okay, so as I mentioned, there's actually two lines for Franklin Electric solar pack. There's the photon and the subdrive. And we'll go over the differences in a little bit, but the main primary difference, one of the two primary differences, is that the subdrive controllers have an optional AC input for a standalone generator or an auxiliary generator. You can see that on the right image on the lower left-hand corner. The second major difference between the two is that the subdrive goes up to a 3.0 horsepower version, whereas the photon only goes up to a 1.5 horsepower version. They do both come in variable flow rates between 5 and 90 gallons per minute, and they both operate in 4-inch or larger inner diameter well casings as well. Okay, so as I mentioned, the subdrive models go up to about 35,000 gallons per day. The photon models go up to about 24,000 gallons per day. That's due to that 3 horsepower motor model difference between the two. Both use the 4-inch submersible motor, and I will mention that Franklin Electric has an excellent online sizing tool that can simplify and consolidate a lot of the information that we're going to be going over. But of course, it's very helpful nonetheless to understand the pump curves and how everything actually works. Okay, so just like we had the table equivalent for the pump curve for the SDS line, we similarly have an equivalent table for the pump curve for the Franklin Electric pump. In this case, we're looking at a 5 SDSP-0.75 HP pump. From the naming scheme on the previous page, you'll notice that that first number represents the 5 gallon per minute rating. The second letter sequence represents subdrive instead of photon. And then, of course, at the end, this is the 3/4 horsepower version. Okay, so for our example, we're going to go back to our original TDH calculation, our first example of around 141 feet. We're going to, again, choose the next closest one just for reference. So we're going to choose a TDH of 131. We are going to go over to the 900-watt array column just as a reference point. You can see these column headers are the array size, PV power watts. And then we are going to find the flow rate row corresponding to our TDH. So basically 900-watt array at a TDH of 131 gives us an estimated flow rate of 7 gallons per minute. But in the lower right-hand corner of the screen, you can see that that's not the entire story. That is sort of an estimate. So in order to get the entire story, what we need to do is we need to look at the actual pump curve for this pump in question. So you can see up in the left, upper left, 5 SD-SP-0.75 horsepower. So what we're looking at, this point on the screen, if we follow the very bottom x-axis at the 900 mark, which is the PV array size of 900 watts, we're going to go up until we find the blue curve, blue line, going mostly horizontal, that represents our total dynamic head. That is 131 feet. So this red circle is the point at which that 900-watt array crosses the 131-foot total dynamic head line. What's important here is that in order for this to work exactly, we need both the solar array wattage of 900 watts as well as the voltage that's marked in these light blue vertical columns. So you can see we're in between 2 points here. On the left-hand side, we have a voltage curve of 125 volts. And on the right-hand side, we have a voltage curve of 137.5. So these are our bounds. So we know from estimating we need a voltage of around 130 volts or so on this array. So what we're going to go do is we're going to find a data sheet for a module in question, and we're going to look at the real numbers, and we're going to find out what our real-world scenario is actually going to be, because it depends on voltage. So we're going to go and look at the data sheet of a Yingli 320-watt module. This happens to be one that we stock and sell, so it's as good as any others. We look at the max power voltage for the 320-watt module, and we see that it's a clean 37.0 volts. So what we're going to do is we're first going to look at approximately 3 modules in series. So if we might wire those 3 modules in series, we get a max array voltage of around 111 volts. We just told ourselves we're looking for about 131 or 130 volts, so that's a little bit too low. So we're going to go the next step up in size, so we're going to go to 4 modules in series. And 37 times 4 turns out to be 148 volts. We're going to be conservative. We want at least our estimated flow rate, so we're going to go up in size, in this case, to 148 volts. And now our array size is 1280 watts. So we're going to go back to our curve here. And now we're going to look at our starting point compared to what our actual results were for the real world 3 and 4 module array using the Yingli 320-watt module. Okay, in the first case, we said that the 3 modules in series was actually approximately 111 volts. So if we look, we've dropped all the way down to this curve on the left here of 112.5 volts. Now, if we follow that intersection, because the voltage is the limiting factor here, and we draw our line over to what our flow rate is on this secondary y-axis, you can see that the real estimate is 5.3 gallons per minute. So we started off thinking that we were going to get 7 gallons per minute at a 900-watt array, but really we found that the voltage is the limiting factor, and we're only going to get approximately 5.3 if we use a 3-module array setup. So we jumped it up to a 4-module array setup and found that the voltage jumped all the way to 148 volts, which is actually right about on this 150-volt curve on the far right-hand side. So now, if you follow the 150-volt curve to the total dynamic headline of 131 feet, you'll see that this is the point that we intersected. And again, we need to check both voltage and wattage. So we have 148 volts, which checks out on the curve. And then if we follow this down to the x-axis, you'll see we're around 1240 or so watts is what is required. Our array we said is 1280 watts. So in this scenario, our 4-module array would produce an estimated 8.1 gallons per minute. Okay. So that's the basic fundamentals of reading and interpreting the pump curves for the SunPumps SDS line and the Franklin Electric subdrive and photon lines, basically using the total dynamic head calculation that we reviewed. So now we're going to talk a little bit about the SunWize WPK that we recently released. Now what these are they are solar kits that are intended to be able to be paired with any SDS, subdrive, or photon water pump, and that has to be the appropriate one, and we'll go over the lookup tables for that. So we have a WPK SP, which are designed specifically for use with the SunPumps SDS line of pumps, and we have our WPK FE, which are designed for both the photon and subdrive pumps. I'll take this moment to point out that we do have some handouts on this webinar. We do have the data sheets for those, so if you would like to follow along, we'll be reviewing some of the critical information on those. So I want to reiterate, as you'll see, we'll emphasize here, that the way that this works is that you order the pump standalone. That's either the SDS pump, the photon, or the subdrive. That's one part number. And then the second thing that you order is the SunWize WPK. In order to have the complete full system, you need both the SunWize WPK and the solar water pump itself. Finally, there are some accessories in order to make this optimal for every installation. It can include some optional things like the float switch and the disconnects, and one critical thing, which is the pump cable length, which we'll explain in a moment here, is driven by the customer and defined by the customer. Okay, so the first thing we're going to go over is what are the WPK SP, the SunPump series WPK. So you'll see here that we basically have 5 models. We have a 65 watt, a 90 watt, a 140 watt, a 160 watt, and a 220 watt array. And these correspond to support various SDS pumps, and we'll see that in our lookup tables in a moment. What do these kits comprise of? If you look on the left-hand side, you'll see that there's a black and a red marker. Everything in the black section above the red line is required equipment included in the WPK, and then below the red line are the optional components. The float switch is optional and the DC disconnect is optional in this case. Now, in our WPK, the WPK itself includes the pump controller for SunPumps. So all you need to do is order the actual SDS pump itself and then the WPK, and that will include everything that you need. As part of that, you need to define what the pump wire length is, because this is going to be dependent on your project and your well depth. We can, of course, support you with that, but if you know what that is, you simply specify that length at the time of order, and you're good to go. Okay, so the next WPK that we're going to go over is the Franklin Electric series. These are substantially larger in size and now use 72-cell solar modules, large format 72-cell solar modules, excuse me, and they come in 3 to 8 or 9 module configurations to support various pump sizes from that 3/4 horsepower rating up to 3 horsepower. They all come with a top of pole mount rack from Solar Rackworks. These will fit with adapters 2-inch to 8-inch schedule 40 diameter pipes. 4 to 8 are the most common. And it also includes the output cable from the array, as well as the combiner box for the solar arrays to put all the modules in series, and the circuit breaker for the disconnect. So pretty much everything that you need to wire the power into the Franklin Electric solar pack to have a complete system. All right, so now that we've talked a little bit about what the WPKs are, a little bit of background on the water pumps, as well as understanding TDH, we're ready to look at some of these lookup tables and see how much easier it is to find estimates on your project's flow rate requirements, as opposed to having to iterate through a bunch of pump curve tables. So we're going to start with our SunPumps table here, I will quickly point out the primary features of this. In the first column, you'll see we have the solar pump in question. So that is the actual SDS pump. You'll see that there are several iterations, and those are covered on the SunPump specifications PDF handout that we have attached. The next column in is the total dynamic head column. That should be pretty straightforward. It is in descending depth from small TDH to large TDH. That's your load, quote unquote. And then we have the corresponding SunWize WPK for each row entry. So really pretty simple. You find the row entry in question that you need based on your total dynamic head, and that will give you the pump and the WPK that you need for that complete system. All you need to do is go to these Sun resource columns and find the production value that meets your requirements for your seasonal needs. So the first column here is a Sun resource of 1.0. The estimated flow production, the estimated daily flow production given a Sun resource of 1.0. And then the next column is the water production daily with a Sun resource of 2.0, 3.0, 4.0, 5.0, and 6.0. Those correspond roughly to the seasonal periods of winter, spring, fall, and summer, roughly. So now, in our particular example that we've been looking at, which we show up here on the top left, which was a total dynamic head of approximately 139, with 2.5 sun hours, with an estimated flow production of about 187.5 gallons per day. So the first thing that we're going to do is just sort of do a spitball estimate and look here at our total dynamic head range. So you can see that our 139 total dynamic head value is a little bit in between these values. So we have two options. We can sort of estimate in between. We can take the conservative approach, or we can take the non-conservative approach. So we know that our bounds are somewhere between 3 sun hours, which is the upper bound, and 2 sun hours, which is the lower bound, and somewhere between 116 feet total dynamic head and 230 feet total dynamic head. So we know our solution lies somewhere in the middle of these numbers. So as I said, for a spitball estimate, let's just say that we average these 4 numbers. You get about 256.6 gallons per day, which really isn't that far off of your 187.5 gallons per day without very much work at all. So the next approach that we're going to take is we're going to do the conservative approach. Say that you knew you needed this production as a baseline. You could simply go down to the next highest total dynamic head and find a flow rate that was sufficient at a sun resource that is conservatively sized below your known 2.5. So in this case, if we assume that our total dynamic head is actually 231, we would get an estimated flow rate of 97 gallons per day at a sun hour of 2.0 with an SDS D228 with a WPK SP140. And we know this is very, very conservative because the 231 total dynamic head value is much, much larger than the 139. In reality, the 139 is much closer to 116. So we know that in that case, our flow rates would be closer to between 300 and 470. So depending on what your goals are, depending on what your threshold or tolerance for risk is, it's very easy to, at a glance, choose the appropriate system for your application. Furthermore, it lets you hone in on the right appropriately sized pump if you wish to dig into the pump curves for that specific pump to get more detailed analysis. It helps you drive to the right pump to begin with, rather than having to look through all the various pump curves to figure out which one is going to be optimal in a given TDH and array size. Okay. So now we're going to move on to the Franklin Electric lookup tables. They are very similar with some noted differences. So similarity, on the left-hand first column, we have the water pump model. So just like the SDS pump in question, we now have either a subdrive or a photon pump in question. Now, in our lookup table area, similarly, we have estimated daily flow rate in gallons per day. And then in our middle column, we have our total dynamic head. Our Franklin Electric lookup tables are quite large. There's a broad range of TDHs, so I've boiled this down to just one TDH range. The one in question we're looking at around 130 to 140 TDH. So I've just boiled this view down to that. So you'll note here that there are two numbers for every column of WPK. So these correspond to the 6 WPK sizes that we reviewed in the previous slide. And under every column, every cell value, there are two values. The first value is the estimated winter production, and the second value is the estimated summer production. So what is winter and summer in our cases? They are average months with peak sun hours of 1.5 and 5.5 sun hours respectively. So in our case that we looked at previously, we had a total dynamic head estimate of around 131 feet with an array of 960 watts for the 3-array version with an estimated production of 5.3 gallons per minute. So the calculation was 1.5 sun hours, if we assume that we're in a 1.5 sun hour zone, times 5.3 gallons per minute times 60 minutes per hour gives us 477 gallons per day. Now, if we look at the chart equivalently, we can see that we have a WPK FE 945, a total dynamic head of 130 feet, with the SubDrive 5 SDS P 3/4 horsepower, producing approximately 440 gallons per day in winter. So you can see our 440 number estimate is very close to our 477 gallons per day. And we're going to repeat this exercise for a few more examples. So now let's assume that same example, we're going with the 4-module configuration. So rather than 960 watts, we're looking at 1280 watts. We're looking at our 148 volts, which gives us an estimated production of 8.1 gallons per minute. So our 1.5 sun hours times our 8.1 gallons per minute times our 60 minutes per hour gives us 729 gallons per day. Compare that to our lookup chart of 640 gallons per day. Very close alignment. For the third example, you'll note that we are doing now the 1280 watt array 4-module configuration with the estimated 8.1 gallons per minute option, but now in a 5.5 sun hour zone. So 5.5 sun hours times 8.1 gallons per minute times our 60 minutes per hour now gives us 2,673 gallons per day. Verse on our chart, our estimate, the second value in the cell is the 5.5 sun hours estimate. For the 4-module WPK, it gives us 2,300 gallons per day. So very close in alignment. Now, one thing you'll notice here is that our chart numbers are always conservative, which is done on purpose so that you can always design safely on the right side. And you'll notice here that all these numbers are in close alignment to a D rate. We do apply a conservative D rate to these. So again, that's another safety factor value to know that you're sizing conservatively when using these numbers. Okay, so that covers the lookup tables briefly. So now we're going to move on to the SunTech drive application. So again, now we're going to be focusing just on a controller. All the previous setups that we were talking about before were basically the pump itself integrated with a pump controller that accepts DC input, or in the case of SubDrive, AC or DC input. Now, because those are all integrated solutions, they can handle the electrical interface between the DC input and the motor specifications themselves. In reality, and in the vast majority of applications and examples out there, the water pumps that are being used are single-phase AC, or in some cases, 3-phase AC. Because the solar array produces DC power and the pumps require traditional single-phase or 3-phase AC power, there's a disconnect that exists there between powering traditional AC pumps with solar arrays. There are a couple of solutions out there. The one that we are highlighting and work closely with is the SunTech Drive Pico Cell. This controller is designed specifically to address this application. As you can see from the diagram here, it is very straightforward. It takes the solar panel DC energy and converts that to the appropriate single-phase or three-phase AC power to power any single-phase AC pumps up to 1.5 horsepower and a three-phase AC pump up to 2 horsepower. We'll talk about that in a moment. So as we mentioned, it's not just pumps in this case that can be used. It could also be motors, compressors, or any number of other AC input devices like that. And again, this is a very big deal because in market applications, the vast majority of water pumps that you'd want to address are AC, and this also allows for the retrofitting option. So you can have a traditional typical AC pump out there that's been used for a long time, decide that you want to move it over to solar power, and you can do that very easily. So looking at some of the specifications for this unit, we can see that depending on the AC specifications, the rating of the controller changes. So again, for three-phase applications, at 2 horsepower, you can get up to 6 to 8 amps. And that would require a PV capacity of between 2,300 to 2,800 watts on the array. And then it gives us our minimum voltage max power, similarly to where we reviewed on the Franklin Electric curves, that you need to provide both the array wattage size and the array voltage specifications. And then, of course, they give your maximum open circuit voltage, which is your design limit on the array as well. And then going down in size for 0.5 horsepower motor applications, you can see the single phase 120 or 230 volts except respectively 4.5 or 2 to 4 amps. So this is a basic overview of all the various applications that this one single controller can be used in. Again, this is all just for the picocell 2 horsepower. Very versatile, 50, 60 hertz, 120, 230 volt single phase, 3 phase for a variety of horsepower sizes on the pump. Okay, briefly covering the technical specifications for the SunTech driver. I will mention that one of the cool features about this is that the device is that it combines a lot of different historical devices into one. So it now acts as the MPPT controller for the solar array to get that maximum amount of energy input or energy output out of the array. So again, MPPT operating voltage from the array, it will accept anything between 100 and 380 volts DC with an open circuit design limit of 400 volts. Gives you your maximum PV panel current right there, 9 amps. Your single phase AC motor power limit is 1.5 horsepowers, whereas your 3-phase motor limit's 2 horsepowers. It's got a nice amount of protection within the casing itself, right? It's an NEMA 4 IP66, broad temperature profile for a variety of, outdoor and rugged application uses. And then you can see its footprint factor is very small, only about 10 inches by 5.5 inches by 4 inches. And then it'll give you wire terminal sizes. Okay, so and then of course we have some more resources available on our website. So now we can hopefully open this up to questions if folks have any.
Hey, Errol, we have several questions on linear current boosters. First off, what are they? Is that considered a soft start? And is that included in the pump curve calculations?
Great questions. I'm going to defer to David Love if you have, David.
Yes, the Gail had a question on soft start. It doesn't apply to the SunPump since that's DC direct. However, it does have a linear current booster in the SunPump controller to help start during the start of the day and also run longer at the end of the day to kind of play around with voltage and amperage to kind of maximize water pumping throughout the day. And on the Franklin and SunTech drive, the soft start feature is built into the electronics of both of those, where it does a similar thing with the sort of the MPPT style of fooling around with the voltage and amperage to get it to start during the beginning of the day and end of the day, and also track the max power point of the solar array throughout the day. So was there another question, Rob?
Yeah, the other question was, are those included in the pump curves?
I think close enough. You know, it really, I think it's just a bit on the conservative side, as we found with both of those manufacturers, that it's, you know, it would fall more into, you know, the peak sun hour zone that we use, and, you know, it may extend that a little bit more than that 5.0, but at that point you're dealing with, you know, average long-term weather data versus, you know, actual out in the field data.
Okay, well, I think that was all the questions I saw.
Okay. Well, and then the other thing I really wanted to get out is Errol went into deep, dark detail on the pump curves on the Franklin, and the Franklin website that he showed earlier is a great resource that kind of builds all that into the output report that they provide, and it's a good explanation of why primarily the solar array is larger wattage than, you know, they show as a bare bones minimum.
We have another question that came in. This is a good one, actually. Are any of these UL listed?
Yes, the Franklin is UL listed, and I do believe the SunTech drive as well. The other one that we've used historically in the past, Grundfos, is not UL listed.
Okay, and they're asking for a link to the Franklin webpage for information.
I'm trying, but I need to get out of presentation.
Well, it's a good reminder that this presentation will be saved and put up on the webinar section.
All right,
I hear Errol typing madly, so
yeah. Hopefully folks got that.
Yeah, I see in the chat box now.
We missed a gentleman's question last time because we ended a little bit early, so I'm happy to give folks another 30 seconds or minute or 2 minutes here if they want to ponder, if they have any other questions. I know it takes time sometimes to formulate that and get it into the chat box, so I don't want to rush people too much. We do have a few more minutes.
You want to plug our next webinars?
Well, yes, hopefully we'll have more announced, but I do think the Industrial Control Panels webinar, which is the next one that we have coming up, I believe that's scheduled for February 28th. I think that's going to be an excellent webinar. The control panel design and what the control panel entails really speaks the story for most of the system design work that we do. So I think that'll be very educational for folks.
Somebody had a question about how can they buy the pumps from SunWize, and I would say contact your account manager. If you don't have one, go ahead and just fill out an online questionnaire, and we will refer you to a salesperson that's appropriate for your area.
Jamie, let me put in a question or a response here in the chat. At the bottom of our website, in the footer section, we have direct numbers for all of our senior sales executives. So you can literally just go to our website, scroll to the very bottom, and find the direct number for a variety of sales folks. If you don't feel like dialing through the 800 number system.
Let's see. Somebody also has, in the meantime, somebody also has a question. Can you add a battery to the SunPump SD pumps if you have limited sun resources?
Let me jump in there on that.
I have my opinion too, but since you guys are handling this, I'll let you take that one.
The SunPumps is 24 volts, and yeah, you can add a battery bank to that, and it really has to do with kind of how it's going to be used. The SunPumps if it's going into a water tank, is daylight hours only, fills it up, done with it. Once you add a battery, you have to size it as any other industrial off-grid load. It's 2.3 amps times however many hours per that day. So you can size a system in that regard. And there have been a fair number of off-grid battery-based pumps with the SunPumps that I've done over the years, primarily in really low water applications where, like for a restroom for the park service, they know they need 200 gallons a day, and it only runs as operated, and then it's got either a float switch or a pressure switch to only run as needed. Because if you have to size the water pump system as a battery system running continuously or during a certain number of days, it gets a lot more expensive with the batteries needed to operate that for that time frame. And that it's generally, like Errol said earlier, far, far simpler to just store water instead of electricity. So out of the water pumping systems that I've done, battery-based systems probably represent less than 3% of the ones I've ever done.
Okay, we also have another question on float switches. What are the float switch options? I guess was the question.
I'll jump in there. I wrote in chat, and I don't know if it's 100% right, so I want to double check. There is a singular float switch option for both SunPumps and Franklin Electric. Is that correct? You either get it or you don't get it, and you get one option if you want it.
Yeah.
Is that correct?
Yeah. Okay. Yeah. I think the idea behind this is simple. If you're using if you're using a tank, the idea is that you don't, well, I guess the option is all it does is shut the pump off when the tank gets full. I guess the other option is you don't want to do that. You can just have an overflow and it just dumps water onto the ground or whatever. But it's just there to shut off the tank when it gets when it's full. That's all.
And there are two types of water float switches, which might be the question, is either normally open or normally closed. And I know for certain that SunPumps and Franklin can use either one of those, and it's just a setting within the controller to tell which one, when for it to turn on and when for it to turn off. And then I would have to check on the SunTech drive to see which version, normally open or normally closed, is needed for that controller.
Perfect, thanks.
Yep, good point. We have another question. Opinion on using a direct DC pump as a piggyback support for an installed AC sub pump in a well.
You can do it. I'm not quite sure the motivation behind it, but it's just a matter of it's a completely separate system that you just need to have enough space in the well casing to drop down another pipe and pump and just run it completely as a separate system. And that's also one of the reasons for retrofitting with the SunTech drive of a 110 volt or whatnot is that you could do that externally as wiring and doing some sort of transfer switch between the two if you want that sort of approach without getting it into a plumbing project. So that's one of the beauties of using the SunTech drive is it's a solar and electrical project and don't have to drag the plumber out.
All right, well, we got 1 more minute. I guess we'll give people a last opportunity here to get in any lingering thoughts. Keep prodding people. It seems like they keep asking questions. So.
We'll see. We do have one more question. Let's see here. Says so you could have a standard pump if water is needed at night, or emergency, and the DC pump is down the well just above the standard.
I was actually going to ask about that as well. If you had enough space below the water table in the well casing, could you put like 2 4-inch pumps stacked vertically on top of each other, more or less? Is that how you do it, I assume?
I mean, theoretically, I've seen people do this with some pumps and residences, actually, in case you lose utility power as a battery backup. Sometimes they build it in the one pump, and sometimes they put 2 in. I mean, you can do the same thing in a regular well as well. It's just the concept still applies. It can still be done. It's just a matter, as you point out, whether there's space to do it or not. That's the big question. I think David had the other point, though, of it's probably better to use one of the pumps that can do both AC and DC. It would make it a lot easier and simpler to do it that way. I guess anything else to add to that, David?
Nope, that'll do. So how's that look for questions?
I think that's pretty good, David.
Yep, I think that's it.
Perfect.
Well, I just want to thank everybody for joining us. We really appreciate you having here, and hopefully folks make it out for our next webinar on February 28th on industrial control panels, as well as any others that we have in the future as well. And as always, we're here to support you.